Welcome to lecture 3B of Power Electronics. We were discussing the rectifiers. In lecture 3A, we discussed the introduction of diode rectifiers. In this lecture, we will focus on the single-phase half-wave rectifier circuits. The single-phase half-wave rectifier circuits will require a transformer. In the transformer, the primary voltage is denoted by Vin and the secondary voltage is denoted by Vs, and this is basically a step down transformer with 1:n ratio. So the secondary voltage will be less than the primary voltage. After stepping up the voltage, we have a diode which is connected in the network and different loads are connected in the network. The diode will be forward biased when the input voltage Vs is greater than the diode potential, and it will be reverse biased when the input voltage is less than the diode potential. So two important topologies are possible. One is the topology A, where we have the resistive or the capacitive load. So the load which is connected in the rectifier circuit may be the R load or it can be the RC load. The next topology which is possible in the load circuit can be the inductive or the RL load. So we can have the RL load or L load. Here we can see that there are two diodes, D1 and D2, where the D1 is the main diode and D2 is basically the freewheeling diode which is connected to discharge the power or the energy which is present in the inductor L. So this we going to discuss in more detail. So the role of the freewheeling diode D2 is basically it required to provide a path for the trapped kinetic energy which is present in the inductor to discharge when D1 is reversed biased. So if the diode D1 is reversed biased, then the diode D2 will be forward biased. In that case, all the energy which is present in the inductor will be discharged when D1 is reverse biased. Second, it allows the inductor current to freewheel through it when D1 is off. So when D1 is reversed bias, the current will be circulating between the load and the diode D2. The transformer configuration which is connected between the mains or the grid voltage Vin is applied at the primary of the transformer. So here we have the primary voltage and the secondary voltage of the transformer is N into Vn, where N is the transformation ratio. The choice of the turns ratio N depend upon the load voltage requirement. So how much voltage we required at the load end, that will decide how much secondary voltage we can have at the transformer secondary. So the transformation ratio N will be appropriately adjusted. Now these two topologies A and B, let us see the operational dynamics. So when the dot poles of the transformer are positive, so here we have the dot poles and both are positive, the D1 will conduct, so it is forward biased and the load voltage follow the secondary voltage of the transformer. So here we have the load voltage and here we have the secondary voltage of the transformer. The diode D1 is basically forward biased when the dot poles are positive. However, the D2 in topology B, here D2 which is the freewheeling diode is reverse bias and it is off during this time. So there is no role of D2 in the network. All the current will be flowing through the load and the source. When Vs goes negative, so if the source voltage is basically negative, so we are dealing with the negative voltage with respect to the dot poles, the D1 is reversed biased, so it is off, and then the load being the inductive in nature will be free wheels through this diode D2. So D2 will come into picture only when the B1 is basically reverse biased. So the single phase diode rectifier may have different load configurations. Let us discuss the R load in this particular lecture, and then in the coming lecture we will discuss the other type of loads. So in the load, we have connected only the resistance R, and V0 indicates the average output voltage. The current flowing through the resistor is I0, which is the average current, and there is a diode which is connected in the network, and this is basically single phase, so only one phase will be there in the input voltage. And this is also the half wave rectifier because we have only one diode connected. And this is a step down transformer with ratio 1:n, so the secondary voltage will be less than the primary voltage. If we define the secondary voltage as a function of time t, then we can write this one as sinusoidal function Vm sine omega t, where omega is nothing but 2 pi f, where f is the frequency of the supply. So what happened to the sinusoidal voltage? Vs. The sinusoidal voltage has the maximum magnitude Vm, which we can see here. This is maximum magnitude Vm, and it is the time period, let us take to be 2 pi. So you have the time period which is equal to 2 pi with the negative magnitude is equal to minus Vm. So the voltage V0, which is the output voltage, will be having only one half of the positive half cycle of the source, and there is no negative half cycle. So here you have the forward biasing of the diode, and here you have the reverse biasing of the diode, which we can see in the diode potential. So the diode potential, here we have the forward bias, so it is in the on state, and here you have the reverse bias where the maximum potential of minus Vm is applied in the diode. The current will have the same shape as the voltage, so V0 and I0 will have the same shape, but its maximum magnitude will be equal to Vm by R. So whatever the value of the resistance we are connecting, that will give you the current I0. If we are solving for the average value of the output voltage or the load voltage, so the output voltage average, because the time period is 2 pi and it is conducting from 0 to pi, so the input is given by Vm sine omega t d omega t, and then if we integrate from 0 to pi, we are getting Vm by pi. So putting the appropriate limit from 0 to pi, because pi is the conduction period, we for one half cycle. So when we have the one half cycle of the input, so here we have Vs, it is conducting only for only one half. So this is what the output voltage we have. So it is 0 to pi. When we talk about the RMS value of the output voltage, we know how to calculate the RMS voltage. This we have discussed in detail in circuit analysis. The RMS voltage is nothing but the square root. So it is the square root means 1 by 2. So you have the 1 by time period, this is time period, and you will be having 1 by time period integration from 0 to pi, and then you have the source voltage Vs whole square dt. So here you have V square sine square omega dt. If we integrate from 0 to pi, putting appropriate limit, we are getting Vm by 2 as the RMS output voltage. So the average voltage is Vm by pi and the RMS voltage is Vm by 2, and this we are discussing only for the resistive load. When we talk about the load current I0, so I0 is nothing but the average voltage V0 divided by R, and the average voltage is given by Vm by pi, so it is Vm by pi into R. And if we calculate the load current in terms of the RMS value, so it is RMS voltage by the resistor, RMS voltage is Vm by 2, and then we divide with resistor R. What is the peak value of the diode current? The peak value of the diode current is nothing but Vm by R, which is similar to what we have the peak value of the source voltage. And if we talk about the peak inverse voltage, so what is the peak inverse voltage? The peak inverse voltage is the maximum voltage that appears across the diode in the blocking state. So what is the meaning of blocking state? The blocking state is the reverse bias condition of the diode. So here the peak inverse voltage is Vm, because you can see that when the diode potential was plotted, first the diode will be conducting, and then you have the entire reverse voltage. So these voltage, whatever we have, which is equal to the Vm in the negative direction. So you have Vm, and Vm is nothing but root 2 into RMS value of the transformer secondary voltage. So if you can have the transformer here you have the secondary voltage. If you multiply that with root 2, that you will be getting the peak inverse voltage, or otherwise we can say that the Vm is the peak inverse voltage of the diode. When we talk about what is the power delivered to the resistive load, we know that power formula is basically product of voltage into current. So the average or the RMS voltage multiplied with the RMS current, if you do, then we get it, the power is equal to Vm square by 4R or Vs square by 2R. Whatever we can use it from the secondary, this is from the secondary concept and this is from the maximum concept. So it is equal to the RMS current square into R. So I can say that the power is nothing but the product of voltage into current. So this is the RMS voltage and the RMS current, or it is equal to RMS current square multiplied with the resistor R. And the input power factor, if you want to calculate, so that is equal to power delivered to the load divided by what is the volt ampere input condition. So power delivered to the load or the resistive load, we have calculated VOR into IOR. This is the RMS voltage and the RMS current product divided by input volt ampere. So which is the input voltage is Vs, secondary output, multiplied with the current IOR. So if we do that, the current will be cancelling out. So it is VOR by Vs, and the RMS voltage can be written as root 2 into the secondary voltage. So Vs and Vs will cancel out, and you will be getting the power factor as a constant value 0.707, and this is under lagging condition. So this completes this lecture where we discussed on the rectifier circuit and only with the resistive load. In the coming lectures, we will discuss more on the different type of loads, like we have the inductive load, capacitive load, RL load, RC load, or the load along with the DC source known as RLE load, and what is the role of the freewheeling diode. So let us discuss more in the coming lectures. Thank you for now.